Today we're going to look at finding the determinants of matrices. We'll start by looking at the most basic 2x2 case. Now, how would we find the determinant of this matrix? So if we split up our diagonals, then if we take the product of A and D and take away the product of B and C, we'll actually get the determinant of this matrix. And this is the generalised formula for the 2x2 matrix. Moving on to 3x3 matrices, it starts to get a little bit more complicated. We're going to start off by doing something quite strange, but you just got to stick with it. So we're going to duplicate the first two columns and add them to the end to make this 5x3 grid. Now, taking the A, B and C elements of the original matrix and circling around the diagonals, and similarly doing the same thing but with the G, H and I elements, we get this pattern. You may be wondering how we're going to find the determinant using this. Well, starting with the green diagonals, we'll look at the first one. If we take the product of A, E and I, then add the product of B, F and G, and finally add the product of C, D and H. Then, looking at the red diagonals, if we take away the product of G, E and C, and take away the product of H, F, A, and finally take away the product of I, D and B, we actually get a generalised formula for the determinant of our original 3x3 matrices. This process of finding a 3x3 determinant is also known as the rule of saris. Now this is all good for the 2x2 and 3x3 cases, but what about the generalised n by n case? Well, for this we can use a general development formula, which I'll put here. The process of using this is a lot easier to display using an example. So for example here, I'll develop a 4x4 matrix. This formula actually allows us to develop a matrix along a row. So we have to choose a row to develop along. I'd usually recommend developing along the row that has the most zeros, in this case row 3. So now that we've got our matrix and we've got our formula, we'll firstly expand the summation to apply to this matrix, where I is the row and j is the column. Right, so let's expand this for each j from 1 to 4. This might look quite complicated, but we'll break it down bit by bit. For the -1 to the power of a number, we know that even powers will give us 1 and odd powers will give us -1, so we can reduce it down to this. Now we're going to replace our A31 element with the corresponding value, similarly for the A32, the A33 and the A34. You can now see why we developed along the row with the most zeros, as we can just cancel out this term. Moving on, we're left with this A tilde notation. For this first case, it's surrounded by the element 3, 1, so if we highlight that 2, then if we highlight the row and column that it's in a separate colour, then the A tilde matrix is just everything that's not highlighted. Now that we've done the first one, we can start to pull out the A tilde matrix for the other two values. Notice again, it's just visually everything that's not on the same row or column as the element that we've chosen. The A tilde matrix only has one row and one column less than the original, so we'd still have to develop the new determinants. Here you could use the rule of saris or the general development formula to find these 3x3 determinants. I'm just going to give the final values for each of these determinants, but feel free to try them. So the first one gives us 11, the second one gives us -16, and the final one gives us 24. Now we can just work all of this out and find that the general determinant of the original matrix A is just 30. Hence, we have found the determinant of this 4x4 matrix. With that general development formula, you can also develop along columns if you just swap the I and j in the formula. I hope you found this video useful today. If you have, please like the video and feel free to subscribe. If you have any questions, just pop them in the comments and I'll respond to you as soon as possible. Cheers.